to the n and an inner problem, right? So you can ask for a linear map c to the n to c to the n, v, and you want that, we have a subspace v, so image of v is v, and the orthogonal projection, so phi is orthogonal, is an orthogonal projection. If the kernel of phi is v perfect. Yeah, so it's just a map from C to the N to a subspace, where it's, so the picture that you have is like this. You have your V here, and then the kernel is supposed to be this thing, that's V perp, and the point is that the orthogonal projection is this. It make sense? It's what you learned in 221. It's orthogonal projection. It is a projection. That means it's mapping onto a subspace, and it's orthogonal, meaning that it's filling the orthogonal space, the thing you're projecting onto.
So, so like an orthogonal projection matrix would be like a matrix T such that like T times like a vector, let's say like X in Cn is like that takes it to phi of. Okay.
It's just that the orthogonal projection in this basis E is the matrix T.
Oh.
Yeah, it's the matrix for an orthogonal projection. And so you can ask for an orthogonal projection. This doesn't have to be C to the N, you know. This definition doesn't require this to be C to the N. But if you want a matrix, which is what you ask, then you have to give a basis. And I'm just saying that that there it is in this basis. Yeah.
Is this equivalent to V minus VV?
V minus? Okay, you mean take away? You mean set remove or subtract?
Subtract.
Okay, V minus?
VV. Dot.
Dot?
Yeah, with the dot product. It's in the
parentheses around the whole thing or not?
Yeah, the inner product.
Around the whole, so like this.
Right. Then VV.
Is it a little v? Is this a little v or a big v?
Little v.
Oh, thank you. Okay, now I can add.
Equal to 0.
Yeah, that should be pretty much the same thing. I'm just thinking of the picture over here. So if this is v, right, and then this is VV, then when you subtract it off, you're taking this guy over here. So it ends up in the orthogonal complement.
With the following definition, I think we need phi to be surjection on phi. Because
that's what I said. I said the image of phi is v.
Okay. Okay.
V is contained in C to the N. We all good? Okay. So I'm going to assume for this lecture that you remember what the characteristic polynomial is, and what geometric multiplicity is, and algebraic multiplicity. There are reminders of these things in the lecture notes and all over the place in the readings that you've been seeing. But I want to talk about Jordan form. Now, we did cover Jordan form in Math 221 at the very, very end in 2019, but we did not in 2020 because the semester was 1 week shorter, so we just didn't get to it. So if you took 221 last semester and you have not seen Jordan form, I hope you've done a little bit of reading about it beforehand, but you did see the geometric multiplicity and algebraic multiplicity and that sort of thing. So let me just give up some items that we're going to fix. So we're going to fix a vector space, V over our field F. So let me write it this way. And that way there can't be any confusion with it being a quotient. And I want the dimension of V to be n, and I want n to be finite. So I'm talking about a finite dimensional vector space over a field. I'm going to have a linear transformation phi from V to itself. And and it has a matrix A, which is going to be phi with respect to some basis E. That's going to be a matrix with entries in the field F. It's an n by n matrix with entries in the field F with respect to a basis in E, which is going to be E1 up through En. So you can think, if you like, that V is just F to the n with this basis. That's the same thing as choosing a basis. Choosing a basis is the same thing as choosing an isomorphism with F to the n. Okay, so here's the Jordan form theorem. So Jordan form. Now, you will also sometimes hear this called Jordan canonical form or Jordan normal form, whatever, it all means the same thing. So it says, let's assume that all eigenvalues, lambda, lie in the field F. That is a non-trivial hypothesis, right? Because it could be, the field could be the real numbers, and you could have I as an eigenvalue. So this is a non-trivial hypothesis. So then V has a basis B such that the matrix of phi with respect to the basis B is block diagonal. And remember what block diagonal means. It means that it looks like this. So here's your matrix, and it's got a square block there, a square block there, maybe a small square block there, and a big square block there, maybe a normal square block there. So it looks like this. It's got zeros outside of those, and the rest on the diagonal, those are square blocks. And this is what it means for a matrix to be block diagonal. It would be diagonal if all these square blocks had size 1. It's block diagonal even if these blocks have bigger size than size 1. It's block diagonal with each block being what's called a Jordan block. And the Jordan blocks look like this. They look like a square matrix here, and that's going to be D by D. And it's going to have lambdas down the diagonal, like this. And then ones above all those lambdas, like that. And the rest is 0. So it's got lambdas down the diagonal, it's got ones on what's called the super diagonal, and it's zeros elsewhere. The Jordan block of some size D for some eigenvalue lambda. Okay, so that's the main part. There's one other sentence that's going to say that this stuff doesn't depend. But so the point is that in 221, we tried to say things like the matrix is diagonalizable if and only if. By the way, when is the matrix diagonalizable? What's the condition that we have for diagonalizability? Anyone remember this? Yeah, Ben?
The geometric multiplicity and algebraic multiplicity of each eigenvalue is the same.
Right, yes. Yeah, so the geometric multiplicities and the algebraic multiplicities, so G of lambda equals A of lambda for all lambda if and only if phi is diagonalizable. Right? But now, so what happens in more generality? G of lambda, the geometric multiplicity, what's the relation between the geometric multiplicity and the algebraic multiplicity? Remember that this is the number of independent eigenvalues with eigenvectors with eigenvalue lambda. And this is the number of times that t minus lambda divides the characteristic polynomial. So what's the relationship between these?
Less than or equal.
Yes, this is less than or equal to in general. So let's just look. So let me write the last sentence of this theorem first, and then we'll just look at it for a second. So the multiset of blocks, by which I mean the d's and the lambdas, right? So each block has a d and a lambda associated with it. If I just look at which pairs lambda d occur, then I can rearrange these blocks as the point. That's all I can do. So the multiset of blocks, that is without listing them in the order from upper left to lower right, that multiset, it depends only on phi. Not on the basis B. That is, whatever basis B you choose to make it have this form, to make the matrix look like this, you will always get a matrix that looks like this, but with the blocks perhaps permuted. Okay, so what does this mean? So let's look at this G of lambda equals A of lambda, or G of lambda is less than or equal to A of lambda in terms of this matrix. How many eigenvectors with eigenvalue lambda come from this block?
However many eigenvalues are in there.
Well, if I look at, so if I had a two-dimensional space of eigenvectors, right, then I would see a block of size 2 by 2 with just multiplied by lambda. See, the only block that I have where something is just multiplied by lambda is this upper 1 by 1 block. The first basis vector is multiplied by lambda, right? And if I look at the last basis vector, it's multiplied by lambda, but then added to the previous basis vector. And the previous one's multiplied by lambda, but added to the previous basis vector, and so on and so forth. So I'm not getting any other eigenvectors with eigenvalue lambda, except for the one that comes from this upper left-hand corner. So here, G of lambda is 1, but A of lambda is D. That's what's going on here, right? So the difference between the geometric multiplicity and the algebraic multiplicity exactly comes from the fact that the Jordan blocks have size bigger than 1. If the Jordan block had size exactly 1, then G of lambda would be 1 and A of lambda would be 1. And then you'd have a bunch of them running down here. But if you have blocks of size bigger than 1, then each time you take the difference between the size of the block and 1, that's giving you how much the difference is between A of lambda and G of lambda that comes from that block. So that's how you should maybe the first go through of how you interpret what the Jordan form theorem says. Now, I didn't write this down in the notes, but I should have. So I'm going to take a picture of it. Of course, there's always the video I can watch. By the way, the videos are posted in the resources part of the web page. Part of the Sakai page, sorry. Okay. So what does this mean? So I want to talk about the meaning of this theorem in sort of abstract vector space land. Yeah, that's the meaning in terms of stuff that you saw in 221. So first of all, let's talk about how you can guarantee that all of the eigenvalues lie in F. So if I gave you a real matrix and I said, okay, find its Jordan form, what would you do? Well, you would try to use this theorem, but you might come upon the problem that some of the eigenvalues are not real. What would you do if the eigenvalues aren't real? Well, if they're not real, what are they? They're certainly complex, right? So if you can't find the Jordan form over the real numbers, allow yourself to find the Jordan form over the complex numbers. the worst that'll happen is that you'll have the eigenvalues sitting, the complex eigenvalues sitting along the diagonal. There's sort of no choice. You can't do that with real eigenvalues, but with complex ones you can. So why is it that the complex numbers always work? So F is algebraically closed. Raise your hand if you've seen this notion before. Almost nobody. Okay, so this is new. If every polynomial with coefficients in F, that's our field, has a root in F. I believe I made all those lines. You all see that on online? Yeah, good. So that definition implies that in fact, if that every polynomial has the form some scalar times t minus alpha, let's call it lambda 1, t minus lambda 1 to the n, what am I calling, n1 up through t minus lambda r to the n r. That is, every polynomial has all of its roots in F. Well, why is that true? Well, if every polynomial has one root in F, then once you have your polynomial, it has that root divided by t minus that root, and now you have a polynomial of degree 1 less, that has a root divided by t minus that root, you have a polynomial of degree 1 less, and so on and so forth. You keep going this way. Yeah, so having one root, so saying that every polynomial has one root in F is the same thing as saying that every polynomial completely factors as a product of linear factors times a scalar. Okay, so this implies the hypothesis of the Jordan form theorem. Okay, great. So if your field is algebraically closed, then you can use the Jordan form theorem without having to worry about it. So here's what's called the fundamental theorem of algebra, which most of you haven't seen, or let's just have a little bit of fun. Raise your hand if you've seen the fundamental theorem of algebra. Right, good. It's a proper, not a proper, it's a subset of those people who raised their hands before about having seen algebraically closed. And the fundamental theorem of algebra says that the complex numbers as a field is algebraically closed. I will not prove that here. It lies outside of this course. It belongs in an analysis course or maybe a topology course. It uses the fact that the real numbers are complete, and that you can draw curves in the complex numbers. There are all sorts of proofs of this thing. Actually, you can prove this by Galois theory too. There's a nice Galois theory proof of this. But they all have to use the definition of the complex numbers, which relies on, therefore, the definition of the real numbers, which is the completion of the rational numbers. So something non-trivial has to go into the statement of this theorem, into the proof of this theorem. That's the idea here. So we're not going to prove it in our linear algebra class, but we will assume it because it's true. Okay. So now the question is, what does block diagonal mean? So that's just a statement about, okay, how can you ensure that that all your eigenvalues lie in F? Well, if you're given a real matrix, then you should allow yourself to use complex numbers, and then you're fine automatically. Okay. The same thing, by the way, works for, say, finite fields. All fields have algebraic closures. It is always possible to find an algebraic closure of any given field. So you can always, if you allow yourself to use more scalars than you had before, you can always use the Jordan form theorem. But things get really interesting. And if you want to understand how things get interesting, then you should take Math 401 or 501, where you will study finite fields and field extensions and these kinds of things. So here's the definition of direct sum. It says V is V1, and that's an O plus V2. So that's backslash O plus. So it's a circle with a plus inside of it, or a plus with a circle around it. That means, raise your hand if you've seen this before. Not so many, okay. It means that V is V1 plus V2, and I assume that you all know what that means. It means that you're allowed to, so V1 is a subspace, V2 is a subspace. V1 plus V2 is everything you can get by adding something in V1 to something in V2. That's, I hope, by now standard. And V1 intersect V2 is 0. Okay, so this says you have two subspaces with trivial intersection whose sum is all of V. So proposition. This is the same thing as saying that V has a basis B, which is going to be B1 union B2. I don't have to write disjoint because since it's a, well, do I have to write disjoint? Let's write disjoint. I'm going to put a dot in there to say that this basis is a disjoint union of B1 and B2. Because otherwise, you'll see in a second. And I want that VI is the span of BI for I equals 1 and 2. So that says that B1 is the span of B1, V2 is the span of B2, and V has a basis that's B1 union B2. And I just wanted to make sure that in order to make V1 intersect V2 0, I wanted to make sure that these bases were disjoint. I didn't want to accidentally copy any of the basis vectors. Because I'm writing this union as a union of sets and not as a union of multisets, I could have avoided this problem by writing V equals B1, comma, B2. So you concatenate the list that comes from B1 and from B2. And then if there were a repeated element, this couldn't be a basis. But if I want to write them as unions of sets, then I have to write this union as disjoint to prevent myself from listing an element twice. Okay, the point, another way to say this that would have avoided the problem is to say that V has a basis B with a partition into two subsets, B1 and B2, such that B1 is a basis for V1 and B2 is a basis for V2. It's a partition, it's the point. You're taking some of the basis vectors and putting them into V1 and some of them and putting them into V2. Now, is this the same thing as saying that V1 is orthogonal to V2? V1 orthogonal to V2 implies that V1 intersect V2 is 0, but it does not, there's no condition the other way, right? You can have subspaces whose intersection is 0 without them being orthogonal. So I don't want you to think of this as being V1, that V is the direct sum of V1 and its orthogonal complement. That is not necessarily what we're talking about. You can, if you're over a field that allows it, choose an inner product to make V1 orthogonal to V2. But there's no reason why, if you're given an inner product, V1 has to be orthogonal to V2 already. So the picture is that you can certainly have, so inside here you can have a subspace there, that's V1, you can have a subspace there, that's V2. And these are not orthogonal subspaces, but it is true here that R2 is V1 direct sum V2. And everything in R2 can be written as a sum of something in V1 and something in V2. And V1 intersect V2 is, if I draw this dot fat enough, 0. But these spaces aren't orthogonal inside of R2. Not with the standard inner product anyway. Right. So you can do this for more general sets, not just pairs of subspaces. But let's do just one example with two. So F to the n is always going to be f to the m direct sum f to the n minus m. What did I write? I wrote the right thing, which is the span of E1 up through EM, direct sum the span of EM plus 1 up through EN. Yeah? There you go. Questions about direct sum of two subspaces? Definition: V is the direct sum of more subspaces, V1 up through VR, and I'll tell you that this R is, I guess, related to this R over here. It needn't be actually the same. The number R here is not going to necessarily be the same as the number of blocks here, because some of the blocks might have the same eigenvalue. The R there is counting the number of distinct eigenvalues. The number of blocks here is going to correspond to the number of V's over here. That's if V is V1 plus VR. So everything in the vector space V can be written as a sum of vectors, one in each of the VI's. And we want that VI intersected with the sum of all j not equal to I of Vj. We want that to be 0 for all I. So one way to say this would be that you want V to be the sum of all the VI's, and you want the direct sum, so you want the sum decomposition. So yeah, I could break this sum up as, say, VI, and then plus V1 plus VI minus 1 plus VI plus 1 plus VR. So there's two spaces, right? There's VI and then the ones you get by omitting VI, and I want that sum to be direct. So it's just saying that it's a direct sum of pairs in all sort of possible ways. That if you take any subset of the VI's, you separate them off, and you take any other sub, then you take the complementary subset, then V is the direct sum of those two sums.
Professor Miller.
Yes.
So when I think of a basis vector for f to the m, I think of, or basis vectors, I think of vectors of length m. And then correspondingly for f to the n minus m, I think of vectors of length n minus m.
Don't say length, say with m entries.
Okay, with m entries.
Right.
And so I'm kind of confused on like how we're adding these vectors together if they have a different number of entries.
Does that help? So f to the n is just the span of the first n basis vectors.
Mm-hmm.
And I'm taking f to the n minus m to be the span of the last n minus m basis vectors.
Mm-hmm.
So I renamed the basis vectors. So here the basis vectors of f to the m are called E1 up through EM.
Mm-hmm.
If you take a vector that's a linear combination of E1 through EM, you'll get a vector that's in f to the n, but only its first m entries can be non-zero.
Okay.
If you took a linear combination of these guys, you'd get a vector in f to the n, but only its last n minus m entries could be non-zero. Its other entries will be 0. So I've called those subspaces f to the m and f to the n minus m, even though technically they are isomorphic copies of f to the n and f to the n minus m that sit inside of f to the n.
That helps. Thank you.
So the proposition here is that this thing is that this is if and only if. So V is the direct sum of V1 up through VR. That's if and only if V has a basis B with a partition B is B1 union VR with VI is the span of VI for all I. Right? So the direct sum, you should think of a direct sum as being, I can choose bases so that a basis of the big one is a union of bases of the small ones. The disjoint union. So for example, V has basis V1 up through Vn. That's if and only if V is equal to the span of V1 direct sum the span of V. This is the diagonalizable case when the V's are eigenvectors. This is going to be the case where the Jordan form is going to be diagonal. This is where the basis that we're going to choose is going to have is going to consist of blocks of size 1. And then the proposition is that phi is block diagonal if and only if V is equal to V1 direct sum up to direct sum VR with phi of VI is contained in VI for all I. And this little thing here, that says that VI is phi invariant. So let's think about that for a second. So you've got these blocks. Let's redraw our matrix like this. Right? Think about what this matrix means. It means that you get 0 outside of here, 0 outside of here, and you've got sort of stuff in there, and 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 stuff in there, right? So think about the basis now. So now you've got a basis, and in this basis, you're saying that when you apply phi to the basis vector V1, it only involves the basis vectors that come from V1 up through VD, like this, right? If I apply phi to any of the first D basis vectors, I'm going to get non-zero coefficients only on the first D basis vectors. That means that phi preserves V1. It takes V1 to V1, right? So here V1 is the span of V1 up through VD, right? That's what this block means. The fact there's a block here means that there's zeros down here, zeros over here, so nothing else gives you a non-zero coefficient on V1 through VD. And phi of V1 through VD involves no other basis vectors other than V1 through VD. Okay? And I'm going to write dot, 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 because if I did the same thing with, these basis vectors, I don't want to give them names. And these are the same basis vectors, I don't want to give them names. Phi of these basis vectors only involves these basis vectors. So that's what it means for phi of the VIs. So VIs are supposed to be phi invariant for all I. That's what it means to have a block matrix. It means you've got your vector space written as a direct sum of subspaces, and phi is acting on each of the subspaces sort of independently of the others. in a true sense of the word independent, linearly independently of the others, right? It's only involving its own basis vectors. Okay, so now what do the Jordan blocks actually mean? So this proposition tells you, hopefully, what the Jordan form theorem means when you say it has a block decomposition. It means that you can choose a basis of V so that something, and the something is that, well, each of the blocks is saying that there's a subspace of V that phi preserves, right? It's phi invariant. And the fact that the blocks are nice is going to tell you something about these invariant subspaces. So this is all about how the vector space decomposes. Now the next part is going to be about what each of these blocks looks like, and therefore what each of these VI feels like as a vector subspace of V. Other questions so far? Okay. So now the question is, what do the Jordan blocks actually mean? So let me start with the Cayley-Hamilton theorem. The Cayley-Hamilton theorem is probably the shortest theorem we're going to state in this course. There it is. It says that if you take the characteristic polynomial of our linear transformation phi, and then you plug in phi, and you get 0. So this will be explained more in the proof as to what this actually means. But think about what it means to plug in a linear transformation into a polynomial. You did some exercises like this in 221 where they said, so for instance, in problem 12 that Selene was asking about earlier, right? The point was that you had things like a squared equals a. A squared equals a means that a squared minus a equals 0, or that if p of t is t squared minus t, then p of a is 0. Right? This is what it means for a matrix to be idempotent in this way. It means that it's a root of the, when you plug it into this polynomial t squared minus t, you get 0. This is going to show that the t squared minus t is going to divide the characteristic polynomial of a, actually. That's what it's going to show. This has to be, this is going to be the minimal polynomial of a. That's what this t squared minus t is. It's going to be the minimal polynomial. We'll get to that in a few minutes. So proof. Let's fix a basis. And let's call it E1 up through En of V, so that phi, when you apply it to the ith basis vector, well, what's that going to be? It's going to be some linear combination of the basis vectors, right? But we're just going back to the very first days of 221 when we wrote down matrices. Matrices were giving you coefficients of the images of basis vectors after you apply linear transformations. So here, phi of EI is going to be some linear combination of the basis vectors. Let's call it AI1, E1, plus AIN, EN. Okay, what is that? That's going to be a row, AI, times the column E1 down through EN. Now, this may make you a little bit uncomfortable. The entries in this column are not scalars. The entries in this column are elements of V. These are elements of the vector space V. They are not scalars. Okay? Nonetheless, this is certainly true, formally speaking, right? This is going to be a row like this. This is the row AI, and here's the column. That's the column E1 down through EN, and this row times that column is that linear combination, formally speaking. Agreed? Okay. So what does this imply? This implies that if I look at the vector phi E1 down through phi En, that this is equal to A times E1 up through En. That's just this statement up here. It says phi EI is this linear combination of E1 through En. And so now I'm saying, what's phi E1? Well, it's the first row of this matrix times E1 through En. What's phi of En? It's the last row of this matrix times E1 through En. And what's the ith row? It's AI times E1 up through En. Okay, so this is just a formulation of what it means to have written phi in coordinates. Okay, great. So by definition, so if you don't remember what the characteristic polynomial is, here's what it means. This is going to be the determinant of A minus phi I. Yeah? In general, if I put a variable here, p phi of t, this can be the determinant of A minus ti. So if I'm plugging in phi, then I'm going to take A minus phi I. This is a linear transformation. I can take its determinant. Linear transformation from V to itself, so I can take its determinant. Good. So what I need, what am I supposed to be proving? I'm supposed to be proving that this polynomial is 0. Right? I want that when I plug in phi into the characteristic polynomial, I actually get 0. This is whatever it is, whether it be 0 or not, it is a linear transformation. Right? Just like when I take a squared minus a squared minus a, it's a matrix. It gives me a linear transformation. It's the matrix for some linear transformation. Right? When I plug in phi into a polynomial, whatever polynomial, what I get, at the very least, is a linear transformation. I would like that linear transformation to be 0. How do I demonstrate that a linear transformation is 0? Well, I have a linear transformation from V to W. That linear transformation is 0 if and only if it sends a basis of V to 0. Right? So I need that all the basis vectors go to 0. So what I need is that P of phi, when I apply it to EI, I get 0 for all I. That's how you tell the linear transformation is 0. You get 0 if and only if, when you apply it to a basis, you get 0 on every basis vector. Equivalently, yeah, question?
So what is the object of the determinant is in this case?
What is this kind of object?
Yeah, the determinant of it. Because,
What is the determinant? The determinant is a scalar.
but if what I'm confused about is that you're taking the characteristic polynomial of a linear, and then you're applying it to a linear transformation.
Yes?
And you're multiplying that by a basis vector. You're applying that.
This guy over here, this is a linear transformation.
Right, so the determinant should also be a linear transformation, not just a scaling. Because
Well, okay. So the determinant is going to be a linear I don't want to get it to we'll do this in the last week of the course. Technically, the determinant is going, so wait a minute, I fixed a basis, didn't I? Yes, I fixed a basis, so the determinant is a scalar. Technically, the determinant, let me do an aside. Just a little aside, which you'll understand much later in this course, like in the last week. But technically, the determinant, so if I have, let me call it C, maps V to W, let's call it V to V. Then I have now, let me call it W, because I fixed the basis of V already. So if I have C maps W to W, I do not need to fix a basis. Then let's say the dimension of W is D. Then the determinant is actually a map from wedge D of W to wedge D of W. That's technically what the determinant is. It's not actually a scalar. You're right, it is a map, but it's a map. So the thing is that dimension of wedge D of W is 1. So this is now a map between two vector spaces of between the same vector space to itself, where the vector space has dimension 1. How do you take a linear map from a vector space of dimension 1 to a vector space of dimension 1?
Scalar multiplication.
As soon as you choose a basis, it's scalar multiplication. It takes an element here to there's how do I say? I mean, I could choose a basis here and a basis here, so that the basis vector here went to the basis vector here. But if I choose a single basis vector here and here, then it's given by scalar multiplication.
But
that scalar is called the determinant.
that in general, though, just applying the characteristic polynomial to phi
Yes.
is not a dimension one.
No, this is just a homomorphism. It is some homomorphism, and furthermore, it's a homomorphism from V to V.
Right, so when you say it's equal to the determinant, that's the part that
I see what you mean. So this is, let me say it this way.
okay.
Fair enough, point taken. Did I write that in here or not? I did not. I need the I there. I'm going to use it actually shortly. Good. So equivalently, this is now back to the proof. I'm going to take that last statement that I wrote down, which is P phi of phi applied to EI is 0 for all I, and I'm just going to write it out as a matrix. Here it's going to be P phi of phi down through P phi of phi, and now I'm going to apply it to E1 down through En, and that's supposed to be 0, 0, like this. Right, and this here, which is what Will was saying, this thing here, that's P phi of phi times I. Better?
Or is it the determinant times I?
No, this is P phi of phi times I. Oh, I wrote the wrong thing. I wanted this to be det. This is wrong in the notes. I want this to be det of this down through det of that.
Yeah.
That's wrong in the notes. So I have to make a note for myself. Fix this. Is it? Here it is. Fix that. Okay. And fix. Let's put the I there. Good. In the end, this is going to come down to something really simple. We have to get the notation right. So this is det P phi of phi times the identity. Okay? Now, what is P phi of phi? What is det P phi of phi? Wait a minute. P phi of phi.
You need that of A.
No, this is, I actually want this, oops, I think this is actually right as stated. I want P phi of phi. I actually do want P phi of phi. I don't want the determinant of this thing. I want it to actually be 0. I had this right before. This is P phi of phi times the identity, but another way to write that would be as det K minus phi I times the identity. So I'm putting a linear map. This is a linear map. This is not a scalar. This is a linear map.
That's fine, but it's just that the determinant is a scalar. That's, it's just,
No, this determinant is not a scalar. This determinant is a linear map.
okay. But with dimension one, as we were talking about.
No. This determinant, so here, the determinant, let's do it this way. Let's do another aside. Another aside here. So det of A minus Ti, right, what is that? That's a polynomial. Right? P phi of T. So that's a polynomial. And I'll write it in F bracket T. So it's a polynomial with coefficients in F.
Okay, so then I think originally you don't need it times I then.
Yeah, well, no, I don't. I think that's right. I don't need this. Right, so this is actually a linear map from V to V.
Yeah.
Right, so when I take this polynomial and I plug in phi, P phi of phi is a map from V to V. This thing is P phi of phi times the identity. So think if I put t's in here instead of phis, I don't think anyone would be confused. I'd be putting a polynomial in this entry and a polynomial in this entry. Right? This would be a polynomial times the identity, which means I put the polynomial all down the diagonal. If I now plug phi in, now I've got linear transformations down the diagonal, which shouldn't bug you any more than putting the entries of this column being elements of V. So the entries of this column are elements of V. The entries of this matrix are linear transformations from V to V. Right? So these are linear transformations from V to V, and these things are elements in V. Good. So I think I should, I should maybe explain more, but I don't think what I wrote in the notes is wrong. I think it's actually right, but one has to look at where all the elements lie. Okay, so this is the determinant of A minus phi times the identity, right? What is the determinant of A minus phi times the identity? That's going to be C transpose times A minus phi itself, and that's here, where C is the cofactor matrix of A minus phi. And again, if that bugs you, then make this A minus ti, then make the cofactor matrix of it, and then plug in phi afterward. Right? We've written down determinant of A minus ti many, many, many times in the past. And I'm just saying do that, but then at the end replace t with phi. So we know what it means to write down the cofactor matrix of A minus ti. So just do that and then put phis instead of t's. Okay. But see, I've got this equation that now says that def A minus phi times I is equal to 0. That's what I'm supposed to get, right? So I have C transpose A minus phi times E1 through En. So let's look at this equation. Let's look at the equation A minus phi times E1 through En. What is this? Well, this is A E1 up through En minus phi E1 down through phi En. What is this equal to?
0.
Why?
Well, based on the definition, the basis that you chose there.
No, the definition is this thing right here. That's this equation. This equation literally says that this one minus that one is equal to 0. So now you just multiply by the C transpose and you're done. There you go. But so it comes down to this little thing, is that when you make this little calculation, the statement by definition, right? It just says that A applied to each of E1 through En gives you phi of E1 up through phi of En. This is just definition of notation. There's actually nothing that's happened but notation here. And the point is that if you view this as A minus phi applied to E1 through En, right? You view this as A minus phi times E1 through En. If you just multiply that on the left by the transpose, by the transpose of the cofactor matrix, it's still 0. So really not much is going on. It's just sort of understanding what all the notation means in the proof. Yeah, so you took something that was already 0, right? A minus phi applied to E1 through En. That's already 0. Should I multiply it on the left by something? It's still 0. That's all that's happening. Okay.
I have a question.
Yes.
So why the determinant of the A minus phi times I equal to C transpose A minus phi? Can you explain that?
Because this is true with the t instead of a phi. And this is true about determinant. So the determinant of any matrix, right? So the determinant, what's a name for a matrix that isn't A? How about determinant of V? is equal to the cofactor matrix of B transpose. So determinant of B, sorry, this way, determinant of B times I is this. This is something we proved in 221. Right, what we actually proved was the determinant is, so if you take 1 over, oh, well, these things can be 0. Yeah, so this is essentially what we did to write down the formula for the determinant. It's the cofactor expansion of the determinant. That's what this thing is. Yeah, so look up cofactor expansion or something like that. But when we did it in 221, this is what we actually proved. Okay. Right, so here B is just A minus phi, that's all. Further questions?
So like the matrix A minus Ci, here A is the matrix with element in F. So phi is the linear map. So what does it mean by subtract?
Does it mean A minus phi times I?
Yes.
So A is you'll view A as a linear transformation from V to itself in this basis. So A minus phi is really, what is A minus phi? So again, A minus Ti, we have no problem with this, right?
Yes.
This is a matrix whose entries are polynomials. Then all I'm saying is replace T, replace that with phi. Now what you have is a matrix whose entries are linear transformations.
Okay.
And what you should do is, so what is a scalar? So how is A a matrix of linear transformations? So the point is that Aij is the transformation, multiplication by Aij, which maps V to V.
Okay. So matrix A is also regarded as a matrix with linear
Yes,
linear maps. Okay.
that's right. Yeah, that's kind of hidden in the sort of little trick where you plug in phi for T in a polynomial. Because if I just plugged in the identity, right? So A minus Ti, if I plugged in 0, right? If I take A minus Ti and I plug in 0, what do I get? I get A, which is still a matrix whose entries are linear transformations. So if you were willing to believe that A minus phi, but if you're willing to believe that A minus phi is a matrix whose entries are linear transformations, then if phi is the 0 map, then you should still believe that A is a matrix whose entries are linear transformations.
Okay, thank you. That helps.
Yeah. Good.
I have a quick question. How is
Sure.
phi? How is phi different from A? Like what? I'm kind of confused on what the difference actually is between these two.
A is a matrix, phi is a linear transformation. So I can view A as a matrix whose entries are linear transformations, like Zheng was just asking, right? Zheng was just asking about how do you view A as a matrix full of linear transformations? You can, but to start off with, A itself is a matrix, right? It's just a matrix of scalars. It's defined by this. And phi is a linear map. So A is the matrix of phi with respect to the basis E. Now you might then ask, how do you take A minus phi times the identity? And the answer is that you have to view the entries of A as linear transformations from V to itself. How do you view an entry as a linear transformation? It's this. It's multiplication by that scalar. Multiplication by a scalar is a linear transformation from V to itself. So then the point, the main point is not what's the difference between A and phi. It's what's the difference between A and phi. How do you view those as the same kind of object? The way you view them as the same kind of object is that this is a matrix, phi, whose entries are linear transformations from V to itself, And A is also a matrix whose entries are linear transformations from V to itself. And I didn't cheat, but I sort of slid some things under the rug by saying that we're all used to writing things down like this, and no one has ever asked me, TI, what is that? Well, it's a matrix whose entries are like, polynomials, and A is just a matrix. So why can you add those things? My point is that if you can form A minus TI, if you are then allowed to plug in phi, then you can plug in phi at this level. But when you do that, you're viewing the entries of A as linear transformations from V to itself. Implicitly, because you can plug in T equals 0. Fair enough? Garrett, did that answer the question? He hasn't moved in a long time. I wonder if his video is off. Like, literally, I haven't seen an iota of movement. Okay, is everyone else still online? Give me a wave. Okay, you guys are still there. Garrett, if you're there, can you give me a wave? Okay, he's not there. Oh, so his video has done something funny. Okay, when he comes back, he can ask again. Right. So I wanted to find minimal polynomial. We might not finish this today. And that's okay. We'll just continue next time. A minimal polynomial of phi or A is a monic polynomial. Monic polynomial means that the leading coefficient is 1. M of t of minimal degree satisfying M of phi equals 0 for M of A equals 0, if that's the situation that you're in. Okay? So when we had the A squared minus A over there, that was the minimal polynomial. E.g. A squared equals A implies M of t is going to be A, it's going to be t squared minus t. Generically speaking, it could be that A is the 0 matrix, in which case the minimal polynomial is just A. Or it could be that A is the identity matrix, in which case the minimal polynomial is actually A minus 1. Is T minus 1, sorry. But generically speaking, this is going to happen. Right, what's that saying, by the way? It's saying that a projection has eigenvalues that are 0 or 1. As long as you have both a 0 and a 1, this is the minimal polynomial. If you only have zeros, then the minimal polynomial is t. And if you only have 1s, then the minimal polynomial is t minus 1. But if you have both, then it's t squared minus t. So proposition. One, there exists a unique minimal polynomial. 2, if you have so f of phi is 0, then M divides F. So proof, I claim that 1 follows from 2. Why is that? It's because if M divides F and the degree of M equals the degree of F, then F is alpha M, which implies that that because you required the minimal polynomial, a minimal polynomial to be monic, it implies in fact f equals m. Right, because I required that a minimal polynomial have minimal degree. So if there are two of them, then they have to be scalar multiples of each other. But because both are monic, the leading coefficient is 1, that means that they have to be equal.
Is f always a polynomial?
Yes. Two. Let's assume that f of c is 0. That's right. So we are not assuming that m is unique. We are just assuming that phi has a minimal polynomial, right? So, okay, why does it have a minimal polynomial? I claim that phi, or a, whatever, has a minimal polynomial. What's the proof? So I know that there is a polynomial that when you plug in phi, you get 0. Yeah, Ben?
Because 0, function 0.
No, because it's monic. That's a good question. I meant to actually mention that. This implies that it's not, that it's not equal to 0. Good, okay, so there's a non-zero polynomial that you can plug phi into. What is it?
The characteristic.
The characteristic polynomial. So there is at least one non-zero polynomial that you can plug phi into that gets you 0. So once there is one, there has to be one of minimal degree, because there's only finitely many degrees below n. So one of them has to be the lowest degree in which you have a polynomial that vanishes on phi. So there is one, right? So let's assume that f of phi is 0. So there is a minimal polynomial. Let's suppose we have any other polynomial that satisfies f of phi equals 0, such as f being p sub phi, the characteristic polynomial, right? So let's write f is going to be q n plus r with the degree of r less than the degree of m. So this is called the Euclidean algorithm. And what you do is you subtract off monomial multiples of m until you can't anymore, right? So what you say is that, well, f is some polynomial of degree that may be bigger than m, right? So then start off with q being a monomial. Just multiply m by a monomial of exactly the right degree to cancel the leading term of f. When you do that, you get the result is a polynomial of degree less than degree of f. So now repeat. Subtract off a multiple of m that kills the leading term. Keep doing that until you can't. So look up Euclidean algorithm. Here. To say why you can do this. Okay, so then 0 is f of phi minus q of phi m of phi right, so why is that true? Why is f of phi minus q of phi m of phi equal to 0? Yeah, because this thing and that thing are both 0. But what is this equal to? What is f of phi minus q of phi m of phi actually equal to from the equation over there? R. This is actually equal to r of phi. So that means that r of phi is 0. What does that mean about r? Yes, this implies that r is 0. And that's because the degree of r is less than the degree of m. There are no non-zero polynomials of degree less than m that vanish on phi. So what we've got left is to say what a Jordan block actually is. let me do the first bit of that, and then we'll continue it on Thursday. All right, so this is, we needed this to say what Jordan blocks actually are, but now let's actually use this to talk about Jordan blocks. So I've got a Jordan block, which is going to be a matrix. It's going to be all right d by d, or if you like, it's going to be phi maps v to v, with the dimension of v being d, and that's whose minimal polynomial is t minus lambda. That's what a Jordan block is. Okay? It's a square matrix of size d by d, whose minimal polynomial is t minus lambda to the d. Okay? So it's a d by d matrix. It's saying it's a d by d matrix whose minimal polynomial is equal to its characteristic polynomial, and it has only one root, and that root is lambda. Yeah? Again, it says that the minimal polynomial is equal to the characteristic polynomial, and it has only one root. Repeated that many times. Let's think about what that means for the minimal polynomial be t minus lambda to the d. So when d equals 1, what can you say? That means that phi minus lambda, remember d equals 1, so we're talking about a vector space of dimension 1, which is a 1 by 1 matrix. It says that phi minus lambda v equals 0. What does that mean? That's the same thing as saying that v is in E of lambda and b b is in E of lambda, which means that if I just take b to be a basis consisting of v, then it has b equals just a matrix lambda. Note, as Alan was asking earlier, this is a 1 by 1 matrix whose entry is a linear transformation from V to itself, if you like, where the linear transformation is scaled by lambda. It's also just a matrix with one entry lambda. It's also lambda times the identity. There's many ways to interpret this 1 by 1 thing. Okay, how about d equals 2? And then we'll stop. So now we have phi minus lambda applied to V, that's capital V, the entire vector space. I claim that that is not equal to V. Why can't that be equal to V? So look at the definition of Jordan block here, right? The minimal polynomial should be t minus lambda to the d. So here we're talking about t minus lambda squared. What does it tell you about phi minus lambda squared? Right, so the minimal polynomial, yeah, it's supposed to be 0, right? Phi minus lambda squared should be 0. So if phi minus lambda applied to V was equal to V, then phi minus lambda squared applied to V would also be equal to V. Say, or else, phi minus lambda squared V, which would be phi minus lambda applied to phi minus lambda V, which would be phi minus lambda applied to V, would be V, which is not equal to 0. Right? So it has to be the case that phi minus lambda has a kernel, or if you like, that its image is properly contained in V. Those are the same thing, right? Having a kernel is the same thing as saying that the image is properly contained in V by the rank nullity theorem. Okay, so phi minus lambda has a kernel. That's what this is saying. Okay, so this implies, so on the other hand, we know that phi minus lambda V is not 0. Why?
Otherwise, the minimal polynomial.
Right, since m of phi is phi minus lambda squared. Can't be 0 because we said we have to square it. So that means that this implies that the dimension of phi minus lambda applied to v is equal to 1, because it's not 0 and it's not 2, so it has to be 1. Right? And this means that phi minus lambda v is in the d equals 1 case. And then we're going to do induction. So we'll do that. We'll start with that next time. But the point is that you're going to start with v. Its minimal polynomial with phi. V with phi. So phi is going to map v to v. Its minimal polynomial will be t minus lambda to the d. But when you apply t minus lambda once, now you're in the situation of the d minus 1 where you understand what's going on. And then we'll reconstruct what the matrix looks like and how to choose a good basis and so on. We've done the hard stuff. The rest is the easy stuff. So next time we're going to start with the fun, let's construct a basis. And it is actually fun. And it's simple, and you'll see where the diagonal structure like this, you'll see precisely where it comes from. So as for your I guess homework next time, figure out what this matrix means in terms of basis vectors, in terms of the basis that we needed for this matrix. We already said it earlier. It's, it takes the last one to lambda times the last one plus 1 times the previous and so on and so forth. But think about that and see how it relates to this. Okay, I'll see you guys next time.